This is part 2 of the 6.4 lecture. So, we just said that the logarithmic function is the inverse of the exponential. So, in 6.3, we graphed 2 to the x. So, we had at -1, we had 1/2. At 0, we had 1. At 1, we had 2. At 2, we had 4, etc. So, our graph looked something, whoops, like that. Remember, it was not supposed to cross the x-axis. I did that by not being able to draw. So let's try that again. It's especially hard on this too. It's even harder than it is on paper. Okay, so it looks something like that. Okay, so to graph the inverse function, we flip-flop the x and the y variables. So for 2 to the x, we had -1 for x and y, sorry. We had -1, 1/2. We had the point 0, 1, and we had the point 1, 2. So for the inverse function, we are going to graph log base 2 of x. And to do that, we flip-flop the x's and y's from the 2 to the x. So we had -1, 1/2, so this time we have 1/2 -1. 0, 1 becomes 1, 0, and 1, 2 becomes 2, 1. So we have 1/2 -1, 1, 0, and 2, 1. So it looks kind of like that. So this one's log base 2 of x, and this one is 2 to the x. Now, we also, remember, have a horizontal asymptote for 2 to the x, right? At y equals 0. Well, that also flip-flops, so we have a vertical asymptote at x equals 0 for our log base 2 of x function. So, if we summarize, if you recall, the exponential has a domain of -infinity to infinity. And it has a range of 0 to infinity. Well, since we flip-flopped the x's and the y's for the log base 2 of x, that means the range of 2 to the x becomes the domain of log base 2, and vice versa. So the range becomes the domain, and the domain becomes the range. Symmetry, neither one has any symmetry. X-intercepts, there's none for 2 to the x, but log base 2 of x has the point 1, 0 as an x-intercept. The y-intercept, the exponential, had 0, 1, and the log function does not have a y-intercept. Okay, both functions are increasing. Two to the x has the horizontal asymptote y equals 0. Log base 2 of x does not have one. Similarly, 2 to the x does not have a vertical asymptote, but log base 2 of x does have a vertical asymptote at x equals 0. So, moving to the next page. Okay, just a reminder, our domain is, for the log function, is 0 to infinity, and the range is negative infinity to infinity. So you notice the domain of a log function has to be positive. So we need to determine what the actual domain is if we start changing from a plain old log base whatever of x. So if we have log base 3 of x minus 2, that means that x minus 2 has to be greater than 0. So that means x is greater than 2. So the domain for that one is slightly different. Instead of 0 to infinity, it's 2 to infinity exclusive. Okay, what about the absolute value? Well, absolute value is always non-negative, right? So that means that the absolute value of x minus 1 is always greater than or equal to 0. So the only time we run into a problem is if it actually equals 0. So the only time that equals 0 is when x minus 1 equals 0. So x minus 1 cannot equal 0, meaning that x cannot equal negative 1. So the domain for this one is negative infinity all the way to 1, union with 1 to infinity. So in other words, all we have to do is leave out the value at 1. Okay, what about log base 7 of x squared? Well, that means that x squared, again, can't equal 0, right? Because x squared is always going to be positive unless it equals 0. So that means x can't be 0. So this one is similar to the last one. We have negative infinity to 0, union with 0 to infinity for the domain. Okay, what about log of 9 over x plus 5? Well, the 9 is positive. So the x plus 5, the only way this is going to not be positive is if x plus 5 is less than 0. So we need x plus 5 to be greater than 0, and then it stays positive. So x has to be greater than a negative 5. Which means we have negative 5 to infinity for the domain of that one. Okay, so reminder of the properties of logs. Again, the domain is 0 to infinity. The range is negative infinity to infinity. The x-intercept is 1. There's no y-intercept. The x-axis is the y-axis, or x equals 0, is a vertical asymptote of the graph. A logarithmic function is decreasing if the base is between 0 and 1, and increasing if the base is greater than 1. And a graph always contains these points. It contains 1, 0, A, 1, and 1 over A, comma, negative 1. The graph is smooth and continuous, which means it has no corners or gaps. So here we have some examples that you can look at for yourself.